professor of civil engineering and former director of the Colorado State University Research Foundation, who will talk to you about some special research work just completed on our campus. But before I do, I want to comment briefly on how private industry has enlisted our aid in seeking additional established systems testing facilities. Looking to the future, as more of our institutions of learning work with private industry, we in the field of education and you in American business can benefit measurably. Knowledge of the needs of industry today and tomorrow serve as a blueprint for our university plants, for their hardware, and for their instructional programs for students to meet those needs. I hope sincerely that we shall have more opportunities to work together on projects such as the one you're about to see. And now, Dr. Albertson.
For many years, engineers, contractors, and utilities have been good with problems of damage to water systems. Often there seemed to be no reasonable explanation for the damage, even though entrapped air was a prime suspect. The damage itself frequently was typical of that caused by water hammer, a dynamic condition in water lines. But it would occur even under apparently static conditions. Now we know that when air is released under static conditions of test pressure, the resulting flow of water in the lines sets up dynamic conditions. And thus, we reasoned that the same fundamental principles as those involved in the classic water hammer could be applied here. We set about then, first, to test the validity of this basic assumption. Next, to determine the actual magnitudes of pressure increase which might be encountered. And finally, to determine how to reduce air entrapment if it occurs in field situations. The research work just completed here at Colorado State University confirmed this basic analysis. And it demonstrated that water hammer pressures created when releasing entrapped air can reach as much as 15 times the pipeline test pressure. Obviously, these greater pressures can and do cause damage to the materials in the systems, for these materials are not designed to withstand such extreme pressures. Now, what may be done to minimize damage that might occur? In answer to this question, 3 recommendations have come out of this study. Number 1, use automatic air release valves instead of manual air release valves at all high points in the line where air might accumulate. Number 2, eliminate unnecessary high points by laying the pipeline to grade wherever possible. And number 3, bleed any remaining air very slowly from pipelines before subjecting them to test pressures. We hope sincerely that the results of our findings will be of benefit to you in the design, construction, and operation of better pipeline systems.
Most people are familiar with the annoying sounds of water hammer, the effect of abruptly stopping the flow of water by closing a faucet. In large-sized transmission and distribution pipelines, closing a valve too fast can cause water hammer. The sudden deceleration which quickly transforms the momentum of a column of water into extreme pressures in the pipe. This pressure in a pipe system can damage pumps, couplings, thrust blocks and elbows, pipe walls, valves, boilers, hydrants. In fact, the system can be subjected to stresses greater than its designed structural capacity, its ultimate strength. This applies to all kinds of pipe materials: cast and ductile iron, steel, asbestos cement, concrete, and plastic. Water hammer is the concern of those who stand to gain the most from the elimination of such effects. The contractor, who must meet the specifications and who wants the least uncertainty in his installation. The owner, who as guardian of public funds wants the most value and maximum system effectiveness for the taxpayer's dollar. And the engineer, whose reputation depends on good system design. Often the engineer will make analyses of the possible effects of water hammer on the system. When he does, he either designs adequate strength to withstand surges, or he reduces the magnitude of the surges by specifying control devices, such as surge tanks, at appropriate points in the system. When a valve is closed, the water flows into the tank, relieving the surge. Entrapped air can cause similar surge effects, but it is not as simple to pinpoint as a cause of trouble because its effects usually don't show up until the line has first been filled for testing. It might take longer than it should to bring the line up to pressure. This is almost a sure indication of entrapped air. When this happens, it's only natural to release the air by opening the air relief valves located at the high points of the line. But if a manually operated air relief valve is opened too wide, it can be dangerous. Suddenly, for no apparent reason in a static line, the pressure may fluctuate drastically. Even if there is no major system damage, the owner might have to accept reduced system capacity if remaining entrapped air has significantly constricted the pipe cross-section. But the answers aren't always that easy to obtain with the necessary precision. Often the effects seem to put the blame where it doesn't belong, on friction losses or the strength of materials used. To shed new light on this increasingly urgent problem, Colorado State University, one of the world's largest university hydraulics laboratories, made available extensive test facilities and graduate water resources programs. Here in the hydromachinery laboratory, studies were conducted on the effect of the sudden release of entrapped air in a closed, static system. A candidate for a master's degree with faculty guidance was assigned to the project. A reservoir tank was mounted at the upper end of a laboratory test pipeline. A 4-inch plastic tube connected the reservoir tank to the main pipeline of 4-inch PVC pipe with ring-tight joints. For easier direct observation, clear sections of plastic pipe were used near the expected area of turbulence. A Borden gauge was placed on the line and a valve for introducing air at the high point. Transducers were mounted at 4 points in the pipe wall, capable of sensing and transmitting water pressures electronically. In the nearby console room, fitted with equipment for a wide range of testing, a Moseley recorder was used to trace a permanent record of both positive and negative pressures. First, as a control demonstration, classic water hammer was achieved with water flowing through the system. Rapid closure of a quick-acting ball valve set up surges generating heavy stresses in the pipe wall. Violent changes in pressure, first positive, then negative, reached 15 times the original pressure before normal damping out occurred. The high-pressure shock wave passed back and forth several times, causing alternate tension and compression stresses. As predicted by theory, the maximum water hammer pressure was directly proportional to the initial velocity. Next, the flow was stopped to set up a static situation in a closed system similar to that during field testing. Air was then injected to form an air pocket at the high point of the line. The ambient pressure showed as a steady trace on the Moseley recorder. A deflecting elbow was installed to drain off escaping water. Then, the air was released as quickly as possible, with the air relief valve wide open, to generate a surge that indicated a rapid conversion from a static to a dynamic situation. At the point, and all along the line, the pressure waves generated resembled those of classic water hammer. This water hammer effect is produced when the air is exhausted, because the water, with 800 times the density of the air, cannot escape at anywhere near the velocity of the air escaping through the valve. Therefore, the water essentially comes to a sudden stop after filling the former air pocket and sets up pressure surges back and forth in the line. The surge pressure is directly proportional to the deceleration of the water column. At higher initial pressures, typical of field requirements, variations of this magnitude could easily generate pressures greater than the design strength of a water pipe system. Then, the tests were conducted at a higher external pressure, in this case, 15 psi. Again, the air was released suddenly at maximum valve opening, with greatly intensified effects along the line. The recorder showed drastic fluctuations around the higher static pressure. Under the same conditions, the stresses were substantially reduced simply by releasing the air more slowly with a smaller valve opening. Obviously, this would be a good procedure in the field, where far larger pressures are the rule, particularly if the relief valves are manually operated. The far less violent surge was also evident on the Moseley trace. The results generally conform to theory and will form the basis of more detailed knowledge for measurement, prediction, and allowance for this phenomenon in pipeline system design. This would also mean more precise recognition of the effects of air entrapped in pipelines, so that the effects could be reduced or virtually eliminated for practical purposes. But first, it is important to know the possible sources of the entrapped air. One obvious source is the air in the pipeline before the line is filled. Often, economic analysis and trade-offs during the design stage will indicate that automatic air relief valves are the most economical in the long run, assuring trouble-free operation. It can also be recommended that wherever possible, the pipe should be laid to grade. This might mean a larger initial installation cost, but it has several advantages. Instead of many high and low points of surface-laid pipeline, the fewer high points can be definitely located when the pipe is laid to grade. Fewer air relief valves will be needed, and there will be less possibility of trouble from entrapped air. Even if no air is present initially, it is important to remember that over a period of time, air may come out of solution as temperatures and water pressures fluctuate, causing air pockets to grow and restrict flow. In a similar and more obvious manner, air can enter the line if vacuum relief valves are installed. These valves help prevent water column separation in the event of power failure, but make no provision to get the air out when normal pressures are resumed. This is one more reason why automatic air relief valves are desirable in system design. Other sources of air in the pipeline come from the flow of water through the line. Sometimes distribution lines or other adjacent lines contain air, which can enter the transmission line, especially when velocities are high. Sometimes these smaller lines are helpful, acting, so to speak, as surge tanks to cushion water hammer effects. But again, there must be provision to relieve this entrapped air. Mounting air relief valves at the start of downhill grades may be only partially effective, as air can tend to collect in pockets on the downhill grade at higher velocities. These pockets should be vented by several outlets located on the downgrade. Many of these effects and solutions have been known for some time. Their importance, however, to the performance of a pipe system is now being realized, as testing facilities give more precise measurements of the effects. These important ventures measure only one parameter of pipeline performance: the effective release of entrapped air from a closed system. It is important to remember that there are other problems beyond this that should be scientifically scrutinized to improve pipeline design and performance. Among these are power and pump failures, air column separation, and field testing techniques. All are promising subjects for subsequent study and more valuable information for the pipeline industry. The results of further studies will have many practical benefits for the owners, design engineers, and contractors who have so much to gain from perfected pipeline performance.
This project, we have with us Dr. M.L. Albertson.
As you may remember, an earlier study of the dynamic effects of releasing entrapped air from pipelines led to three important recommendations for minimizing pipeline damage. Number one, we should use automatic air release valves at all high points where air might accumulate. Number two, we should lay pipe to grade wherever possible to eliminate unnecessary high points. Number three, we should remove air slowly before we subject a pipeline to final test pressures in order to avoid water hammer damage. Now, these are very important general conclusions, but we needed to extend our quantitative knowledge to help improve our field testing techniques. For example, during field testing, what is the proper rate of filling? We know that air should be released slowly, but how slow is slowly? How about transient pressures, which we know from previous research can be far greater than they should be when air is released improperly? We wanted to know more about the effect of different sizes and types of air release valve. It was questions like these that led us to believe that a project studying field testing would be of value, particularly since no systematic data were known to exist on this subject. Jim Andrews, a candidate for a master's degree, chose to make this the subject of his thesis. This film, which you are about to see, is a record of that project.
This is one of the many pressure pipeline tests made under controlled laboratory conditions, part of the overall research project. To explain its objectives, let's take a quick look at some of the hydraulic forces involved. When a pipeline is filled and the air is released at a high point in the line, the density difference between the escaping air and the incoming water causes the water to decelerate rapidly when the water reaches the riser or valve exit, which has a smaller diameter than the main line pipe. This is because the less dense air escapes 28 times as fast as the water. A high pressure wave is generated by the piling up of the denser incoming water, causing an impulsive force as it is slowed. We are concerned with the changes in pressure, delta P in the formula, that might be expected from various rates of filling. In the formula, the change in pressure, delta P, equals the density of the water, Greek letter rho, times the wave speed, small a, times the change in velocity of the incoming water, delta V. The pressure differential, delta P, is affected by several variables. The primary variable is the velocity of the water approaching the high point. Another important variable is the slope of the pipeline at the high point. The degree of flow contraction is determined by the ratio of the diameters of the riser, small d, to the main line pipe, big D. The sizes and types of air release valves were also variable. These then were the leading variables included in this study. The pipeline chosen for field testing was being constructed near Afton, Wyoming. A total of 16,000 feet of large diameter transite transmission line was installed. This low pressure system tapped a snow-fed mountain stream for an irrigation project of the United States Soil Conservation Service. Good installation practices helped reduce the possibility that test results would be distorted by random factors. The 36-inch mainline pipe, 4,105 feet long, drops 200 feet. In the completed line, water enters this diversion structure at the top and runs down through the line to the valley below. The main line divides at a junction T into two smaller lines. Design specifications included a heavy thrust block at the junction and automatic air and vacuum release valves. The researchers studied the relationship of the rate of filling to the test pressures as part of an attempt to develop a valid formula for use in field testing. One of the most important results of the study was the record obtained of transient pressures, particularly the changes during initial filling. Altogether, there were 5 test stations, including this important one at the junction T. In addition to measurements of filling pressures, artificially induced transient pressures were recorded as they moved up and down the line. It should be emphasized that this is not necessarily recommended as a field test procedure. After the field test data were analyzed, we decided that more information was needed on the closure characteristics of the air and vacuum release valves used. A number of these valves were obtained from leading manufacturers and tested in the laboratory. For a valid field testing situation, we used standard 12-inch asbestos cement pipe with the riser and valve exit at the high point. Filling velocities were carefully controlled by a plug valve and measured by an orifice meter. Transducers provided continuous pressure recording at points located 1 foot away and 26 feet away from the high point. In this typical filling test, a 2-inch APCO combination air and vacuum release valve was used at filling rates of 2 feet, 4 feet, and later at 8 feet per second. The rate of flow was established by adjusting the plug valve to pressure readings taken on either side of the inlet orifice, translated into velocity measurements. Another series of tests used different risers, not fitted with air and vacuum release valves. In these tests, the 1-inch riser gave fairly consistent results. The 2-inch riser was less predictable. Even at the lowest test flow rate, 2 feet per second, the transient pressures varied widely due to the dynamic water hammer effect of the air and water mixture escaping through the riser. From our research, we concluded that 2 different types of transients can occur. As shown in this earlier study, the first type is associated with exhaustion of air pockets from manual release ports. This type of transient pressure has a rapid pulse, which may be localized near the air release port. The governing variables seem to be the degree of flow contraction, or small d over big D ratio, also the distribution of air in the pipe. In this study, we found that the second type of transient pressure associated with automatic air and vacuum release valve closures has a more typical water hammer wave, which travels the length of the pipeline. In these tests of automatic air release valves, a pronounced peak in the ratio of pressure change to filling velocity was observed near a rate of 4 feet per second. In general, we found that the pressure rise increased with larger valve size and riser diameters, but valve types made little difference. To sum up, we continue to consider the period of pipeline field testing, particularly during initial filling, to be the most critical in the lifetime of the pipe. This is because the mixture of air and water introduces a large number of variable and transient forces that are not present at any other time. Colorado State recommends that an analysis of the variables and water hammer potential associated with pipeline filling be included in design engineering calculations. A safe filling velocity should be specified, slow enough to avoid transient pressures that would cause damage. At the present time, our recommendation is 1 foot per second or less. The following recommendations may also help to avoid excess pressure changes during filling. Equip the line with automatic air and vacuum air release valves. We prefer the continual acting types that permit additional air release after the main valve is closed. For safe flow contraction, assuring that the incoming water following the escaping air to the valve exit will decelerate within safe limits, we recommend low small d over big D ratios falling in a range of 1/10 to 1/100. These tests are preliminary and are being promulgated for interim reference until more complete results are obtained. The data gathered in this project will be published in useful form for the further guidance of the engineering community and the pipeline industry.